All right, I think that'll work. Okay. All right, as always, thanks for your patience. And so let's finish up here with our unit on this swarm intelligence and sort of finishing up with particle swarm optimization. So just as a recap, we have talked about two kind of chemically inspired communication schemes for swarm intelligence. And that was this ant colony optimization, which, individual ants are basically walking through paths, and each path is a decision vector candidate. And so paths that differ in quality differ in pheromone. And that difference in pheromone that builds up as you get a social group that's climbing over a wide range of paths is what ends up driving the distribution of future choices of what the decision variables are. And so I presented the very basic model of this ant system for Marco Dorigo. Then later, one of his collaborators, De Caro, made ant colony optimization, ACO, where they added things like elitism, remembering where each ant remembers kind of the best path and then decides whether it follows the other ants based on that. And so so that's kind of the modern ACO, is everything we talked about plus a little bit more to improve the performance of ACO. But the kind of nature inspired part of it is just as I kind of summarize here. And then the other very chemically inspired one, which I kind of botched some of the description of, and I really apologize for that last time, was bacterial foraging optimization, which in this case, we have bacteria that are responding both. So they're basically bacteria climbing gradients locally. And those gradients have two parts, and so the gradient has both a component, so that's component from optimization objective, plus a component from, we'll say, cell to cell communication. And then this cell to cell communication can be both attractive and repulsive. And so the interesting interesting difference here is, and I should make this clear because I'm not sure if it was totally clear from the presentation that I gave last time, is that this gradient is defined over continuous space. And so it is also kind of a stigmergic communication channel, in that you can evaluate this gradient. Every bacteria sees the same gradient, but what varies is wherever they are in the decision space. And so if one bacteria is sitting at the same point as another bacteria, they will experience the same gradient. So there aren't any differences on an individual to individual level, but the different individuals contribute a certain amounts of attractive and repulsive chemicals to this soup that they're all swimming in. So really, bacterial foraging optimization is in some ways similar to ACO. In ACO, they're smearing chemical over paths, and each path is a discrete vector that, it's a candidate for your outcome. But in bacterial foraging optimization, it is actually the points in space are candidate outcomes. And a difference here is whereas in ant colony optimization, the amount of chemical you smeared on the space depended upon the quality of the path that you were traveling. In this case, the bacteria are putting out chemicals that have nothing to do with how good or bad the optimization objective is at that point. They are just putting out chemicals to effectively let the other bacteria know where they are. So regardless of where the bacteria is, it's putting out a certain amount of attractive chemical, it's putting out a certain amount of repulsive chemical, and then so as a bacteria deciding where to move, then you can sense the optimization objective, and you can also sense the amount of attractant and repellent that is in that space. And all three of those things come together at one particular point in space. And that tells you whether you should stay at that space or you should move to some other point in that space, try a different candidate solution. And that's how they move around. And then the other addition to that is that they also had this kind of evolutionary component where you can eliminate bacteria, I would say, based on quality of that location. So if you're at a particular location where it's really, really poor, then that bacteria might just clear that one out and then regenerate a new bacteria. And that might be, cloned from another bacteria. It might be just randomly put somewhere else. There are analogies to physical, if let's say a pulse of air went over a colony of bacteria, that might naturally move some from one point to the other. Well, you can also simulate those types of dispersal mechanisms. So you can have elimination and dispersal adding to that, and that sort of adds this kind of evolutionary component. So both of these have a sort of stigmergic chemical, pseudochemical, or I could say chemical communication, but they're using them in very different ways. The last word is, based on, it's supposed to be quality, but my tablet ran out of room. So let me erase that last word here and see if I can write it a little more clearly now that I know what the constraints are. Based, different color, based on quality. So that's supposed to be a Q that starts that word, but I can't quite get the tail of the Q in there. All right, so any questions about these two and the comparisons and contrasts of these two forms, ACO and I'll call BFO, or bacterial foraging optimization? And you can also, if it's easier, you can feel free to use your microphone if anything comes up, chatting as well. Okay, stigmergic, yeah, good question. So this is a term that's a kind of a hip term a lot of people like to use. So stigmergy is the idea that you communicate not by short-term direct peer-to-peer contact, but you communicate by making a persistent change to the surrounding environment. And that persistent change allows for coordination across space and time as other individuals move into that space and detect that you've been there. So you're not communicating with any individual, you're sort of communicating anonymously to whoever comes by that particular region of the environment, and they can detect that you had a presence there. But they don't know who you are, they just know that someone made a modification there. So it's coordination by persistent modification of the environment. And you can contrast that with coordination by direct communication from one individual to another, or one individual to a bunch of others. So broadcast communication, I also would not consider to be stigmergy because it's not persistent. Right now, there are 27 of you logged in. And so when I'm speaking, all of you are hearing me right now. And so you're all hearing me, even though I don't necessarily know who I'm directly speaking to. But I wouldn't call that stigmergy because once I stop speaking, there's no persistence there. Now, if when you all entered, I had a sheet that said Zoom waiting room. And so if you entered a little earlier, you saw that sheet. And if, you know, I would have also allowed you to edit on that, then every time somebody entered, they could make a little note. They could maybe draw a doodle or something like that. And then as more and more people entered, they could see those doodles, and that would maybe give them, you know, insights into how many people have been there, whether the lecture has happened, et cetera, et cetera. And so that's kind of the difference between broadcast communication and Stig merging. All right, how much of an effect is there? How much effect? I'm just reading these out loud because I've got audio recording as well, and so I want to make sure that I capture this. How much effect, or is there a way to visualize what role DH versus W in attraction and repulsion? So now we're getting asked about the hyperparameters in the bacterial foraging optimization. And this is sort of, you know, this is drilling down a little more detail than I guess I want to go into for the scope of this discussion, but so there are these hyperparameters outside the exponential, and then there are these hyperparameters kind of inside the exponential. The ones inside the exponential are weighting kind of space, and the ones outside the exponential are weighting kind of attraction and repulsion in general. So I don't have a good way to say, like, you know, this one is exactly, I mean, I'm not saying there aren't, but off the top of my head, I don't have a great heuristic to give you to say that, you know, if you have this particular problem, you should double this parameter. If you have this particular problem, you should have that parameter. So I don't have an answer to that, but there certainly could be an investigation of that. In fact, that might be a nice final project. If somebody wanted to pick up bacterial foraging optimization and best characterize how these 4 hyperparameters affect the solutions, that would be pretty cool. So, so I'm just throwing that out there. And by the way, with respect to final projects, I think all but 5 people have picked groups. And so it turns out that we will end up having an odd number because we have one person auditing who won't be doing the final project. And so those 5 people who haven't picked a group yet, I've put you in sort of an unnamed group inside Canvas so you can all find each other in case you still are looking for someone. And so if you haven't found a group, go to Canvas and go to the groups option in Canvas, and you should find this like unnamed group, and then you can communicate with each other within that, and then group up. And because we do have an odd number, we're going to need, out of those 5, a group of 2 and a group of 3. So we still have a couple of days to finalize that. Otherwise, everybody else, I've put you in your groups. And if you go to Canvas and click on the groups, you should find some group resources that you can use there for collaborating inside groups. I'm working on getting a Slack page set up for this, but I think because it's a cross-listed course, they're a little confused about how to get it set up and everybody enrolled. But once that's available, I'll make it available. Meanwhile, there are some nice collaboration tools within Canvas. And of course, you can choose other tools. And last thing I want to mention is, if you haven't figured it out, the same commercial Zoom package that all faculty have, students have. And so you can form meetings with your groups over Zoom. When you need to finally record your presentation at the end of the semester, you can actually do the screen recording over Zoom. So you both could be in different locations giving one presentation with it all being recorded through Zoom, and then submit that video up to Canvas when you're done with that. So, so keep that in mind. So with that aside, are there any other questions about ACO or BFO here? And hopefully I answered the question about stigmergy. And if I didn't answer any of those questions, then please let me know. All right. All right, great. So, so we transitioned here, and I'm just step away for a second to turn on a light. So we transitioned then from these 2 stigmergic mechanisms here to things that were based on what I would say would be more broadcast based. And so these 2 mechanisms are, I'm going to put something in the environment and everyone will detect it, but not be able to tell exactly who they're getting communicated from or even when that communication happened. But then when we flip to what we're moving towards, and so I guess I could say this is moving towards particle swarm optimization, then this particular set of strategies was inspired not by you know, ants or bacteria, but inspired by looking at things like birds. And so the idea was, and again, this I mentioned that coming out of the computer graphics community, there were a number of papers actually back as far as the 70s on similar models for how animals move together in groups, be they schools of fish or birds, starlings or wildebeest. So people had made some motion models of these, but they didn't quite get so popular until Craig Reynolds came up with his model. So as I started to say last time, there was this researcher, Craig Reynolds, and this was in ACM SIGGRAPH in 1986, where he introduced the world to what we now affectionately call boids. And so his boids were bird boids, and that was meant to be bird-like objects. And these boids that he, again, this was his attempt not to generate an optimization algorithm, it wasn't to model biology, it was to generate graphics that looked realistic, so that if you were doing animation in the late 80s, then you could very quickly instantiate large groups of individuals that were moving in a hopefully realistic way around a landscape. And so his bird-like objects were pictured as these kind of like little turtles here that have an orientation, and so they can see some distance ahead of them and around them out to some angle. So there's some angle and this distance that's swept out in both directions. And this kind of establishes a topology of effectively communication, but it's more like a topology of awareness. And so maybe I'll put that over here, topology of awareness. And this is very similar to the bacteria we described, where, but in the bacteria case, it's not based on vision, it's based on how much chemical is that you're marinating in. But in this case, it's who you can see within this cone. And so maybe I'll just highlight this region, this kind of visual region that these objects can see in. And then this establishes a kind of, oh, sorry about that. Turn off the option to turn my highlighting into lines. So we have this region, and this region establishes a kind of neighborhood. This region here. And so then you can ask questions, you can then create behaviors, kind of like a little robot that at every time instant it asks, who's in my neighborhood? And then based on who's in my neighborhood, it tells how this boid is going to move. And then when we zoom out and look at all the boids together, then we can say, what patterns do we get with all these boids? And so and so basically you can imagine that on each agent, so on each boid, you then can you calculate some component, and that so then you can say, for all boids in my neighborhood, I consider three things. How much do I want to stay separate from this? So there's a separation to avoid collision. And so this you can think of is that if a neighbor is really close together, there is going to be a large pressure on this Boid to move away from that neighbor. And then there's the second thing is alignment to the average heading. And so these things rotate based on looking at everyone that's in that yellow neighborhood. I calculate an average heading for them and I try to align to them. And if there is any kind of optimization feature here, it's almost that, where you're trying to minimize the difference in alignment across the whole group. So that that isn't what Reynolds was thinking, but later on, people like Dimitri Bersikas, for example, realized that a lot of these algorithms were effectively implementing consensus algorithms where they were trying to form consensus on alignment. And so the studies of dynamic consensus were then used to study these algorithms in terms of using the alignment of each individual as an output. So that's, so if there is any optimization connection, then it would be in this alignment direction. So you can think of this as consensus on heading. But it wasn't meant to be any sort of optimization when it was started. And then this third part is cohesion toward average position. And then you can imagine taking a weighted combination of these. Now I'm going to show you a basic algorithm that does all of these things in sort of a very mathematical way based on one time step. So average heading that I mentioned here. So I was saying that the heading, each Boid has a heading, and that is sort of defined as if I was to define this direction as 0 degrees, then this here you could view as the heading of this Boid. And if we all agree on that this is 0 degrees, then we can then say for every Boid in this neighborhood, then what is the average heading of all the Boids in the neighborhood? And then based on that, you can tweak the heading of the current Boid to move toward that average heading. And then likewise, for the question was, what is average position? And so likewise, for every Boid in the neighborhood, they've all got a position, and you can calculate a centroid of that. That's all of those groups. And so there's going to be other Boids in this sort of cone here, and you can calculate their average position, and you then create an attraction to that average position. So you effectively have repulsion to Boids that are very, very, very close, and you have attraction to the average position of all the Boids. And then you also have attraction in the heading space to, yes, position as position in space. And then you also have attraction to, we could say, the average alignment. And and if you end up writing iterative rules that describe how the position and heading change over time, it turns out that the rules that you write, and I'm about to write one in terms of this so-called Vicsek model, it turns out that those fall right in line with previous mathematics that people like Dimitri Bersikas, I just mentioned him because he's here at ASU, popularized even back in the 70s. And so a lot of these algorithms for moving around like bird flocks, you can, when you write down the math for them, end up looking like algorithms that are seeking to achieve agreement in heading. So just like if you have a bunch of nodes on a network, and they all are trying to agree on what the temperature in a room is, and maybe they keep exchanging temperature and then eventually come to agreement that say, even though I have a noisy measurement of temperature and you have a noisy measurement of temperature, then we're going to average all of our measurements together and come to agreement on an average temperature. Then you can actually think of these agents having random headings, and as they move around in space, what they're doing is they're trying to seek an agreement in heading, the same way those nodes on a network are trying to seek agreement in temperature. And so you can view these these algorithms for flocking as kind of snapshots of algorithms on, I would say, less consistent networks that are trying to do consensus in heading. So you can, so this is some, again, the computer graphics community use these things, and you, and again, I'll show you how to do this in the next page here in kind of a simple mathematical formula, but later on, people like Ian Cousin, who studies collective motion in fish and in birds, has implemented these types of Reynolds-like models in a less mathematical way, in a much more kind of computational way, where you can imagine that each one of these conditions, 1, 2, and 3, trigger kind of different subroutines, and their effect on the motion of the particle is additive. And so if you happen to see that someone is close to you, then that triggers an alignment if they're too close. And if they're too far from you, that triggers an attraction. And if they're, your heading is too far away from the average heading, that triggers kind of an attraction. And yes, the birds are moving kind of forward and closer together. So if you've ever looked up and seen a flock of starlings, and so these are those birds that there could be hundreds of them together, and they seem to fly in a blob in the air. And you almost kind of stop seeing the birds and you just start seeing this blob that's bending and folding and moving around. Then that's what was trying to be mimicked here. How can we build artificial blobs that are moving around? And the direction, that is, so there's a question, how is the direction determined? Well, that comes from this part 2, is that you adjust your alignment toward the average alignment of those around you. So you can picture birds that are trying to stay just far enough away from the closest individuals, but just close enough to sort of the farthest individuals, or all of the individuals are trying to stay in there, but they're also trying to stay pointed in the same direction. So you set your direction in part 2 of this 3-step process, and you kind of set your position or your movement towards a position in start 1 and start 3. So to begin with, they start with random alignment and they converge towards average alignment. That's correct. That's sort of the picture I'm trying to use. It may not be totally pointing in every direction, but yes, they start with random positions and random alignments, and then over time, they move toward each other and the blob starts moving in a consistent direction. And when the blob is moving in a consistent direction like a conveyor belt, then they've sort of achieved a steady state for this system. So they're not, there is no steady state in terms of position. So they'll constantly keep moving, but they might lock into one alignment. And I see, so stimulus is the goal state given direction. I don't understand the question there, but so I don't know if you can elaborate on what you mean by that, but I wouldn't say, I don't want to say there's a goal here, but I just want to say that these are the primitives that define how these things move from step to step to step. And these were an initial model, not of optimization, but just mimicking bird flock. And then is this related to, right now, it's just related to mimicking birds. The optimization component will be thrown in here in just a second when we add kind of gradient climbing. You also, this alignment that they all reach, there is a way to kind of build motion rules that when you come to alignment, you're kind of guaranteed that wherever the birds align, in some transformation of the space in which the birds are moving from, consistent alignment is actually like reaching, you can think of it as like reaching a Nash equilibrium or something like that. So you actually can view convergence on a single heading if you make the right kind of attraction and repulsion forces, as you can turn that into an optimization problem. So if you view it as being important for your particles to be aligned, then you could view this as a mechanism to achieve alignment. You don't know where they'll be aligned, but they will end up choosing alignment. So if you're familiar with consensus or agreement algorithms, then just like I said, you can take these and turn them into a consensus algorithm. Likewise, a lot of consensus algorithms you can visualize like a bird flock moving around. So you can view this as a visualization of a consensus or an agreement approach. And there is no evolutionary component in right now, and there probably won't be in the particle swarm optimization that we get to. We're not going to kill particles, but you could imagine versions of particle swarm optimization that, just like in the bacterial version, will end up killing particles that are sort of like too far out and maybe not doing something useful. But what we'll end up finding here, as I mentioned, a motivation for why the optimization people started even looking at these models is they said that we wanted to kind of keep these optimizers clustered together as they moved through an optimization space coherently. And so unlike the bacteria, where you actually want to spread the bacteria everywhere, but then as they're spread everywhere, kind of cluster them together, almost like a diversity preserving genetic algorithm, here you really do want to keep everybody together. And so there's no reason to kill one of them off. It's better to just move the whole group. And that's kind of like killing them off, but you're not going to kill one and then repopulate. You want to kind of, because then it's going to have to try to lock into the rest of the group. So you maintain cohesion throughout the whole process. The heading direction is not constant. It varies with every time step. And so that's what we'll see in this Vicsek model, but let's do that. And so hopefully that'll answer some of these questions. So one of the earliest kind of mathematical models of this was the so-called Vicsek model. And so there was a paper by Thomas Vicsek et al. And this was in Phys Review Letters in 1995. And this has been generalized in putting on, so I see, I guess this message is more prone to having local optima and various flocks get multiple optimas. We will get to that when, in PSO, we'll see how we deal with the local optima problem. And so there will be a way in which it turns out that if you make your neighborhood very, very large, you'll be very good at finding a local optima and getting stuck in it. But you'll do that very fast. And if you make your neighborhoods very small, you'll be very good at finding a global optima, but you'll be very slow at it. So there's kind of a speed accuracy trade-off deciding how big these neighborhoods are going to be. And we'll get into that when we formally define the particle swarm optimization. So getting there, like one of the kind of early more mathematical expressions of this motion came from this so-called Vicsek model, where Vicsek was trying to sort of add a little bit more mathematical rigor to some of these motions that were being used in like the graphics community and in the movement community in biology. And so the idea here is, let's say I've got particles that, so we're going to use a coordinate frame that, say we're using a radial coordinate frame. And so every particle that's sitting out here in this axis, so it's going to have a particular distance and direction from the origin. So if this is particle I, it has a distance I from the origin, and let's say it's got some orientation that we'll call theta I. And so they each have a, I'll say this is just position R and orientation theta I. And you can think of them as being located at position Ri, moving in direction theta I. And so our question is, how do we update these positions and orientations over time? So in the simple Vicsek model, then we're going to also define a neighborhood, just like we did in the Reynolds model. And so we have a neighborhood size R. And so this is just basically going to be the max distance of interaction between individuals. And so we can then write update rules for knowing your position and orientation at one time, what would be your position and orientation at the next time. And so that might be something like this: theta I at time t plus delta t. So they're physicists, are thinking in continuous time, even though we're taking kind of discrete time sets of delta t, is going to be equal to, and I'm going to use the notation, the average value of the orientation of all of the others at the current time step within some Ri, I'm going to say Ri minus Rj is less than R. So this here, I'm just saying, is some distance metric. So you can think of this as the 2 norm, for example, and this is our neighborhood size R. And this here is just means the average. So we're taking the average. So this here defines the neighborhood. And this is taking the average just over the neighborhood, just of those in my neighborhood. And so my next orientation is going to be, I'm just going to snap to whatever the average orientation currently is. No dynamics there. You can imagine adding dynamics, so you kind of slowly have to reach that, but we don't have that. Okay. So then the next update rule is then how do I get my position? So I can say my next position is going to be equal to my previous position plus some velocity, which is a parameter. You can view them all as moving at a constant velocity. And then times my delta t. So this is kind of the distance. If you think about v delta t, that's kind of the distance you're going to move if you're moving at a constant velocity over this delta t time period. And because r here is a vector quantity, then this is going to be multiplied by the cosine of theta t and the sine of theta t. So we're just projecting this heading along the x and y. And so this is just a vector. And you can think of this as your kind of delta x and delta y. And then what what we would want to add, so this is the basic Vicsek model, and then what Vicsek added here is that I meant to write a little bit earlier, but then highlight it, but I'll just write it here, is that in this orientation, we also add a little noise component. So I've written that in a different color. And so this this eta I t is just some noise. And you can think of this as additive white Gaussian noise. And so each one of them calculates the exact average, and then you perturb it a little bit, and that's what we use in place of dynamics. And then otherwise, the position is this deterministic expression down here. And then those two things together are the basic Vicsek model. So it turns out that the dynamics of this thing are strongly governed by the density of the swarm and the noise amplitude. So to study these things, what Vicsek did and what a lot of others have done since then is they basically just simulated these dynamics in kind of an agent-based model where they're all running around in a toroidal world. So a world where if you walk off one side of the screen, you pop in the other side of the screen. And when you walk up the top side of the screen, you come in the bottom side of the screen. And that makes it very easy to control density. And it turns out that there's a tight balance. So, and I'll get to the question in a second here. So there is a balance between density and noise determines group properties. And so if you get the right density and the right noise, you get cohesive movement. If you get different density and noise, you get something that that never quite orients and almost looks like a bunch of gnats. So you can get toroidal movement, so like you can move around in circles. So there's a bunch of different interesting movement patterns you can get if you move through different regimes of density and noise. And so there's a question, what does the column matrix do, the one after V delta T? This translates, so remember, I guess I could have put a little vector over top of here. Remember that Ri is effectively equal to Xi and Yi. And so this is the position. And so what this is saying here is that, so these are scalars here, and this is a vector here, and this is a vector here. And so all we're doing is we're translating your current position, which is this Ri of t, to your next position, Rit plus delta t, by taking a constant speed that you project along your current orientation. And so that allows you to project it a little bit in the X and less in the Y and vice versa. How does this ensure the algorithm reaches an optimum? It doesn't. This is not particle swarm optimization just yet. This is just a motion rule that's meant us to get us closer to something that we can implement in particle swarm optimization by adding different attraction and repulsion forces. So this is just the kind of bird thing. This just is, again, simulating the same sort of thing that Craig Reynolds was doing. How do you get groups of particles that are constantly moving but trying to strive towards a common alignment? And so future versions of this, later versions, added repulsion, attraction, and alignment regions. And that was motivated by the original motivation from Craig Reynolds' model, where he had these sort of 3 regions. And so you can imagine kind of these circles of repulsion, that's REP, orientation, and attraction, all around each agent. And then otherwise, they're kind of blind to everything outside of that. And these are models that inspired people like, and that were used by people like Ian Cousin in a paper in, say, 2002, where he used these to try to explain the various different structures you see as you move from, say, fish to birds to gnats. So whereas Vicsek was generally interested in self-propelled particles, Ian Cousin tried to then link it more to the biology based on the work of Reynolds and Vicsek as for motivation. All right, so yes.
So do you want to say that it is only by noise that migratory birds migrate thousands of miles away? I mean, it's just by mere chance that you end up doing the right things in a noisy reading, and then you have your trajectory defined such that you make it that far?
No, well, I guess so. This is sort of governing, if we assume that we're just looking at local movement, we're not thinking about large migration. So again, this was thought to be like starling flocks. And so you look overhead and you kind of think that those starlings that are moving and floating around you in these dynamic envelopes, they're not trying to get anywhere. And it turns out that the biology behind this is we think that the reasons why things like starlings do this is there's a principle called the selfish herd. So maybe I'll write that here. And the basic idea behind the selfish herd is that if you are prey, then you are going to be most vulnerable to a predator if you have kind of the largest region around you relative to other prey. And so if you can kind of imagine that if you're a prey item here, and there's a couple of other prey outside here, then these prey are sort of receive some benefit by being close to these other prey, because if a predator were to sort of think about attacking in this region, they could either attack this one or this one. So the so-called domain of danger of a particular prey is sort of in between that prey and the prey that are around it. So this is the domain of danger. And so if you're a prey that is way over here, like this one on the left, then pretty much if a predator were to kind of get close to any of these regions, it is most likely to attack you. So your domain of danger is much larger than these other prey's domain of danger. And so the thought is that, and so you can, for those of you that are kind of geometrically minded, there's a so-called, Voronoi tessellation of space, where if you put a bunch of points in space, then you can calculate these domain of dangers that cut up the space, that partition the space, and in such a way that every point within this region is closest to the centroid of the region and not to any other centroid. And so the Voronoi tessellation kind of makes this measurement formal. And so if you were to take the instantaneous positions of all these animals and then do the Voronoi tessellation, you could then measure the area of each one of these things around them. And then that's how you would formally measure the so-called domain of danger. And so the thought is that there is selective pressure to minimize your domain of danger, which means moving toward other animals. And so you get cover by being in a group. But then those animals are also trying to move toward other animals. And so the thought is that this can generate collective motion as everyone's just trying to stay together. No one wants to be that one animal with a larger domain of danger than the other, because a hawk could come in and it is going to be more likely to attack those that are much larger. Now, nobody's really tested this domain of danger idea until recently, where people actually floated some cardboard that looked kind of like dolphins that were, this is in Australia, and they actually, fixed them in different cluster configurations where each fake dolphin had different domain of dangers around them. And then the sharks that were there would look up at these silhouettes and they'd think they were prey, and they'd see which one got attacked. And time again, it was very easy to predict the one that got attacked. It was the one that always had the largest domain of danger. So there does appear to be strong selective pressure to reduce your domain of danger. So we're not talking about navigation. We're talking about if you're just hanging out in Phoenix and you're flying, then what's the safest way to fly? And the safest way to fly is to cluster around others, because it will be just as likely for them to get hit by a predator as for you to get hit by a predator. And so, so now for moving large distances, that gets much more close to what we're talking about with this particle swarm optimization. So you could imagine that in large distances, everyone knows roughly where to go, but there is some pressure to stay cohesive together. And so, how are those two pressures kind of resolved? And that gets a little bit closer to this PSO. So you can almost think of PSO as moving from the small scale, how do starlings operate above my house, to the large scales of how do Canada geese get from Canada to Arizona periodically. So we'll get into that. Now, there was one other question: is the noise and mutation, noise-like mutation, and V delta T a little bit like learning rate? That's an interesting interpretation. If we do view these things as moving toward different strategies, then there's probably a way to project this onto that interpretation, where this is kind of like the speed of trying solutions. That's kind of like a learning rate. That's like this V parameter. And the noise, I mean, in the case of learning rate, then I would say that, well, noise is like noise. But from a genetic algorithm, it's hard to say what the V is, it's kind of like genetic drift, but not really. So there are definitely probably interpretations you could make, but we just have to be careful because I have a feeling you just end up mixing metaphors. And so you could say, well, the V delta T is like this and the noise is like this other thing, and it's going to be hard to kind of put them together under one elegant framework. All right. So we got the self-assured, we got the Vicsek model. And so then let's see. So the thought was that if we know how to keep things together, then how do we build an optimization algorithm that instead of scattering particles all around a decision space haphazardly, how do we sort of create a group of starlings that's able to search as a blob over a decision space, kind of with the envelope of that blob sort of being a set of solutions they're trying at one time. And then as you move the blob, you kind of move into new sets of solutions to try. And how do you make that good at finding global optima? And so then we get into the original particle swarm optimization algorithm. And the idea behind PSO is that you initialize particles, an array, I'll say an array of particles, so it's still population based, with random positions and orientations. And actually, I'm sorry, I didn't mean to say orientations, I meant to say velocities, random positions and velocities. These, in the traditional PSO, we don't have orientation like the Vicsek model. They're sort of fully actuated. They can kind of move in every direction instantaneously, kind of like a quad rotor or something like that. They don't have to keep moving in one direction. So then for each one of them, we can evaluate. And so the positions are the decision vector candidates. So the idea here is that if we've got 100 particles, those are 100 candidates that we are trying. So we are then going to evaluate the objective function, and we're just thinking of single objective right now, on all particles, or I could say on each particle. So each particle is able to measure how well it's doing. At this point, then we invoke some sort of social communication, and so we compare each particle's evaluation with its, and now I'm sorry, this is where social is part 4, with its personal best, which I will label P best periodically in the future here. So it basically keeps track of what position and what value was best for me. So it basically has a memory of position and value of individual best. And then finally, the social information is that I compare each particle's evaluation with global best, which I will sometimes abbreviate G best. And then, you know, and on both of these, I hope it's obvious that then the outcome of these things would be to update if necessary. So I could say update P best and update G best. And then with all of those, we can finally update our velocity and then update our position. So then step 5, we update position and velocity, which I'm going to do on the next page here. But I wanted to at least write something here to delay the switch so that everybody can see that. We've got step 1, random positions and velocities. Step 2, do your evaluation. Step 3, compare to your personal best and update your personal best if necessary. Step 4, compare to your global best. And by global best, I mean everyone's best. And update the global best if necessary. And then 5, update everyone's position and velocity. And so the way we do that is, so this is our step 5, update step. You could say on each particle, on each self-propelled particle, the next velocity, so v at t plus 1, is going to be equal to the previous v plus some acceleration parameter times, and maybe I'll put a little times there to make sure it's clear it's not a function, times. This here is going to be a, I'm sorry, what is the driving force for the updates? So these are self-propelled particles, and so you can imagine that each particle has a little thruster, just like a bird has got wings, and that they are going to choose how to apply those thrusters. And so they are going to look at their own personal best, they are going to look at the global best, and they are going to look at their previous velocity, and those are going to mix together to decide where they're going to move next. And they decide kind of where to point their thruster in that next direction and move. So we'll see that here in this formula here. So then this acceleration gets multiplied by, and so this RP is a random number between 0 and 1. And that gets multiplied by, and I'll make a note of that here in a second, XIP minus XI. And so XIP is the personal best, and I'll make the note of that in a second as well, plus another random number, different random number, RG, between 0 and 1. And that gets multiplied by XG, the global best, minus XI. And then those things, those all contribute to the acceleration. So I will then just, to make it clear, this here is the P best position. This here is the G best position. These here, this here is a random number. So I'll say it's distributed from 0 to 1. This here is a random number distributed from 0 to 1. This over here is a hyperparameter, and it's acceleration. And I think that's it for velocity. RP are random, but constant across iterations. No, you can view them as being drawn at each iteration. And I would say yes, that normally you would make them different across each bird. You could reduce the computational cost by making them the same across every bird. But for all intents, but for now, I could say in the kind of ugliest, most computationally costly version, we'll just consider them to be different across every bird and across every iteration. And then there's a comment that looks like velocity control. Yes, you can think of this as, like, we're going to add the position here, is that you can think of this as a kind of a single integrator. So if you have a robot that you control its velocity, and then the velocity sets its position, like you can set the motor velocity. This is kind of like motor control. You're setting the velocity of the robot. But you can think of this as vector-based. And so this, I guess maybe I should make a note of that, is that this, you could view this as a vector quantity. So this V could be a velocity vector pointing in a particular direction in space. Do we need? No, we don't need this to be a convex combination. So there's a question, does RP plus RG have to equal 1? Not generally. This is just a conical combination. So we just make them between 0 and 1, and they can be totally independent. You certainly could experiment with versions of PSO where you draw a single random number and you make 1 minus that random number on the other side, so they add to 1. But in general, they can be there. It's 2 degrees of freedom here. Okay, so then the other thing you have to update, well, I could say there are alternative forms. So I could say alternatively, we could have used a different velocity update, which would be like VI t plus 1 is equal to some inertia parameter, which I'll just call W times VI t plus, and then everything that's above without the acceleration. So we can clump that whole parentheses down into this, that whole quantity together, and then I'll say here, no acceleration. In which case, this here, this W parameter is an inertia hyperparameter. And that's actually a very common way to implement this. So what this randomness is trying to achieve, why is it necessary for this algorithm? I see that it will work despite this as well. Good question. So the idea here is we're trying to introduce randomness the same way Vicsek introduced randomness in orientation. And this was just one way to do that, is to sort of say, how much do you trust this attraction to your personal best? And so this sort of allows them to stray from their personal best a little more often. So on average, they kind of have a 0.5 attraction to their personal best, but sometimes they totally ignore their personal best, and sometimes they have a much stronger attraction to personal best. So it's just a way to add more variation. Can you talk on the personal best? What is the mathematic form of it? Do we compare that to some with some notion? So the personal best is, it's just that both the personal best and the global best basically have they have a position, you know, XIP, which you can view as a vector, which is a location. And then there is your evaluation of your function at your personal best. And so this is the kind of evaluation or the quality. And in P-best, you store both of those. Likewise, in G-best, you store the position and the quality of the global best. And then that way, in the update rule, you don't know what the quality is in this particular update rule, but you know where it's located. And so it's how much are you attracted to where the best option was. Can you talk on the personal best and cover that? What is the difference between this velocity and the scalar velocity calculated in the previous slide? So the previous slide, the velocity that we had here, this velocity is meant to be a hyperparameter, which determines how quickly this Vicsek model is moving around. The closest we can kind of view this as pushing this down is thinking the acceleration here is a little bit like the scalar velocity in that previous model. And so that's what I should mention then, you know, maybe make this clear, that our last step is to update position. In which case the previous or the next position is equal to the previous position, and we're just going to say plus the velocity. So we don't bother with any fancy scalars there. And so those are the two things that we update, whether we're focused on updating the position and velocity of every particle based on these relative positions here. So any questions about those update rules? And then after all of this, we can loop back to step number 2, which I'm just going to flip back there real quick to remind us, which is reevaluating our objective function. So that is, you know, evaluate objective function and repeat. And so that's the basic. Where does a direction component fit in? There is no direction component. We view these as self-propelled particles that are fully actuated. And so they can, I guess I should say that the velocity here is vector valued. And so the velocity sort of has a direction to it. It's not a scalar velocity, but we don't have kind of this isn't like a so-called unicycle, where in a unicycle, you're sort of stuck traveling in one orientation and you have to slowly turn your orientation, and that gives you kind of a turning radius. These do not have a turning radius. They, in theory, can move back and forward. Termination criteria, at this point, almost everything we talk about in this class here is a termination criteria will be up to you. So it'll be like, do you want to go for a certain number of steps? Do you want to go until you reach convergence? Maybe you want to go until your global best hasn't changed for 50 steps or something like that. That would be it. So that's kind of arbitrary, and you usually can provide that to the algorithm when you want to stop. All right, any other questions about this update rule? I thought it was a simulation and partly returns on. Yeah, it is. You can view this as this is an optimization algorithm though. And so you can just say we're going to stop it after 1,000 time steps. But there is a goal here that in the end, the global best will hopefully be a good solution to your problem. And maybe the personal best you could view as alternative solutions that aren't as good as the global best. And so I guess I could maybe mention that is that ultimately the output here could be that G best, you could say XG and the corresponding F of XG. And then the F is just an optimization objective. So it's just the standard optimization objective that we've been working on. So you use a genetic algorithm to optimize something, you could use this to optimize something. Does that answer your question? I noticed you unmuted, so.
Yeah, does it use, does it have a connection between all the, what should I say? Does it encode the relation between all the particles in this form?
No, the optimization objective here is just, it's sort of separate. It's like, I want to optimize the number of resistors I put in this particular design, or the type of resistors or something like that. And you're swimming over resistor space, and F is evaluating your design. So F is exactly the same type of optimization objective you put as an input to a genetic algorithm. But instead of using a genetic algorithm, you've decided to use particle swarm optimization. F could be the loss function of a neural network. F is just an optimization objective. It's not related to the particles, but each particle evaluates an F. But that F is related to your objectives, not the particle's objectives.
So let me summarize it. F is specific to a specific particle.
Every particle has the same F, because this is viewed as a single objective optimization algorithm. There are multi-objective PSOs that we won't get to in this class, but you're free to investigate for your final project. And then things get a little, just like they stray a bit, just like GA strayed a bit. But for this purposes, we can view F as the same across them all, and F is supplied by the designer.
Yes, thanks.
Great. All right, so we only have a couple minutes left. So the only thing I have left here, which we can pick up on last time, are variations to this algorithm and how those variations affect the performance of this algorithm. And so, and then also how this algorithm is currently implemented in kind of state-of-the-art implementations in programs like MATLAB and other alternative particle swarm algorithms that have been suggested by the same authors of the particle swarm algorithm that are thought to potentially be better, but have not yet been picked up. So we can probably cover those next time. And then just to give you an idea of where we're going after this, once we're done with this PSO, so we'll probably have half of a class to finish up the PSO and half to start the next section, we're going to start looking into more generic multi-agent systems and the kind of mathematics behind describing things like consensus and how they're inspired by things like opinion dynamics and how we can build algorithms that sort of converge on opinions and how we can study them and how they kind of relate to this. So these were very kind of nature inspired, and the other ones are going to be much more loosely nature inspired, but more kind of built up from the math. And so we'll see a little bit more linear algebra and things like that. I promise not too much, and I'll give you kind of enough that I hope you'll understand the properties that we need to say that things are converging, for example. So any other questions about this basic particle swarm algorithm and how it works, how it's implemented, what the parameters do, and so on? All right. Otherwise, I would just say again, you've all been assigned into your groups that you've picked, or for the 5 of you who haven't picked groups, you're kind of in this kind of fuzzy group that helps you communicate with each other. But if I remember correctly, the group assignment, the choice assignment is due this upcoming weekend. And then I think roughly a week after that or so, you have to submit your choice of algorithm. And that's going to be a very short assignment. And if you pick one that's out of the list that I give you, you've got to tell me which one out of that list. If you propose your own, then a lot of people have been sending emails saying, what do you think about this? And I think that's a great idea to do. And if I give you the okay, you can just put in just a single line saying, I'm going to study, shuffle leapfrog algorithm or whatever it is. If you didn't contact me, then you want to sort of justify why you picked that algorithm and how it relates to the class, and you'll submit that, and you'll do that as a group assignment. So we're at 4:20, so any last burning questions here? Does PSO miss out on some exploration of the decision space as the particles move in a cluster? Yes, and we will see that modifications of PSO are going to allow for more exploration and less exploitation, or vice versa, and that's going to affect kind of the speed and the accuracy of the algorithm. But yes, this is sort of like when you have a premium of only exploring solutions in a cluster together, as opposed to studying a bunch of solutions that are wildly different in parallel. What happens if a project, it's for this semester, I am totally okay with people having the same topic. I would just make sure that what you submit ends up kind of taking your own spin on it. So your demo should be probably different than other people's demos. So if you have conversations with other people and you notice they're doing the same thing as you, try to diversify how you're going to write up your 4-page report and do your presentation. But it's okay with me if 2 people are doing the same, or 2 groups are doing the same algorithm. In an update position, is it all right to add? So I see 2 things. I don't understand the first question about update positions, all right to add displacement with a vector. Then I also see this question, I have a question. So feel free to either write your question or bring, yep.
Yeah, so my question is about the project where, so if we pick an algorithm, do we have to also pick like a task that we would choose on where we are evaluating that algorithm? Or can we choose like a task that was taken previously by some author who wrote that algorithm? My main question is just surrounding, like, do we have to pick like a novel task to implement our algorithm for?
Gotcha. By the way, if anyone wants to drop off, you've got other classes to go to, feel free. We're sort of after regulation here, but I will stick around to answer any questions until 4:30. But to answer this question, I'm hoping that you'll be a little creative. So I would prefer you to simplify the algorithms, to sort of say that the state-of-the-art version of this algorithm does a wide variety of things. We are going to simplify the algorithm and study only these aspects of it. And so creating a simpler algorithm that allows you to come up with kind of a more creative demo I'd prefer you to do that rather than just like finding an article that someone's written about an algorithm and redoing exactly what they did. And if you can make it
Fair enough.
personal, then that's kind of cool. So I've seen people, I remember one really great presentation where somebody built a cellular automaton model where they trained a cellular automaton to reproduce artwork that looked like artwork that that particular student had drawn. So that student drew some artwork of her own. She used that to imprint upon a cellular automaton, and then that used that cellular automaton to draw new artwork and then compared it. That was a really cool project. So that's kind of an example of a personal angle that'd be cool for you to add. Do we need to
Okay.
find an instance of the problem and use an algorithm to solve it with and show results? I would say it'd be nice if you come up with your own demo example, and it can be a toy problem, but at least it just needs to exercise the demons of the algorithm. And so you can say like we are using this toy problem to show how this algorithm gives us tight control over exploration and exploitation. And here's how we show that, for example. When we submit our algorithm choice, is it first come, first serve, a multiple? No, again, multiple teams can use the same algorithm. That's fine. It would be great if we have a diversity, but I'm okay with multiple teams using the same algorithm. It would be, hopefully you'll have different demos. So I don't want you sort of copying what another team does, but I'm okay for multiple teams having the same algorithm.
Professor,
Any
so
other
question?
questions?
Hello.
Hello?
Yeah, Professor. So the question I asked, so it's a bit silly, but in the update portion, right? Aren't we adding a displacement component with a vector component without multiplying with a time component or something of that sort? I'm just trying to understand.
Are you referring to the slide that we're currently looking at here?
Yeah.
So are you saying looking at the velocity, or are you saying the velocity is actually a displacement? Is that what you're sort of saying?
No. So x is position, right? And
X is
velocity
position, and yeah.
Yeah, so we're adding the position with the velocity. Shouldn't it be velocity into time to, make it all the same?
Yeah, right. So you can kind of think of this as having a unit time step that is implicitly being multiplied there. So they just leave that out, and any effect of scaling the velocity is done with the A parameter or the W parameter. So with the acceleration or the inertia. And they kind of figured that if they gobble all that up into that update rule, they don't need to also put it inside the position update rule.
Got it.
So when you're simulating a physical system, then it's really important to kind of get the time scale correct. Here, they're kind of saying the time scale is arbitrary. And so we're just going to arbitrarily say that the delta t here is equal to 1. And that's why it's x plus v as opposed to x plus v times delta t.
Yeah, got it. Thanks, Prof.
Okay, great. Any other questions? All right, I'm seeing more people drop off.
I got
Another question? Yeah, so I see, I saw this one pop up in the chat first. Do you need us to compare the results of our algorithm with a benchmark algorithm? If that is applicable, that would be great. If you want to say, look, our algorithm is so much better than stochastic gradient descent for training a neural network, that's cool. But there will be some algorithms which that doesn't make sense for, like the cellular automaton example. You might be able to come up with like a null model, like if I wanted to solve this problem a different way, here's how I do it. But keep in mind, I'm just looking for these 4-page papers where like, a quarter to half of the paper is explaining the algorithm and the demo is the other half, and you'll have like a couple of references in there. So I don't want you to be too ambitious. So if it really feels like you need a benchmark, then I think it's a good idea to put one in. But if you think you can say something interesting without a benchmark, then it's okay to leave it out. All right, was there another question?
Yes. Professor, I still have a question on the fitness function that you talked about. Did you say that the fitness function is gonna be the same for all the particles, or for all the agents here. So it had, suppose the fitness function had been the distance between the goal state and the state where you are, and or where the particle is, and our objective is a minimization or reducing the error, then wouldn't it be so that all the particles land up at the same place?
Well, I mean that ultimately it's great if the particles all land at the global maximum or minimum of the optimization objective. And so that is a fine outcome. And so, but all I'm saying here is that this F does not relate to any, it has no geometric interpretation. F is purely defining some regions of space as being better than other regions of space. So if F is anything, you can think of F as kind of a height of space. And it's like the particles are running over a landscape and they're all trying to find the top of a hill or something like that. I'm a little hesitant for that because it's hard to run uphill, but if particles had enough self-propulsion that they could all run uphill with easily, with no worries about effort, then the question would be is how does a group of particles find the highest point? And that's kind of what F defines, where that highest point is. Now, we don't know where the highest point is. That's why they have to search for it. So, so everybody is on the same landscape, which means everybody has the same F.
Okay. Oh, well, I'm still not satisfied with it. I'll just look over it a bit and then maybe I'll just drop you an email.
Okay, that sounds fine. And there are some resources online that I've posted on Canvas, and I will I think post a few more in this unit as well.
Thanks.
And I am still holding virtual office hours on Mondays and Tuesdays as usual, and I can make appointments if those times don't work for you. For anybody out there, general comment. So any other questions or concerns? If not, I have another meeting that I have to go to, so I am going to stop the recording and end the meeting and see everyone on Monday or sooner if you need to chat about anything. Great.